Hello, everybody. Today we'll be going over some of the mod best practices. Just a little thing up my side. So thank you all for joining. My name is Ryan Hancock. I'm the Vice President of Engineering. On this call, I'll also be joined by Antonio, who will also be presenting. Antonio, do you want to give yourself a brief introduction?
Hi, this is Antonio Trillas. I'm Director of Engineering with GRISP for the modeling department or mod testing department of the company. So we basically take the models after the facilities are built, and we test according to the mod standards, and we validate the models and fine-tune the models that then are sent to the utilities for their system-wide studies. Okay.
So today we'll be discussing a few main points. First, we'll do an introduction into mod. We, don't know what level of background everyone has for this, so we're going to kind of start very basic, and then we'll kind of get deeper and deeper into the intricacies of mod. So starting with an introduction to mod, and then we'll do a breakdown of what each of the standards that we're looking at are, and then how you can prepare for testing, and then what testing actually looks like. And then lastly, we're going to end on some of the common pitfalls and ways that we can, hopefully avoid them moving forward. So in this section, we're going to, obviously do kind of a basic, very high level description of what is mod and kind of what's the importance of mod. And then, while we're talking about mod, obviously modeling is important. So what type of models are we using in these types of scenarios? So jumping right in, what are mod standards? So to start off, NERC created a set of standards, the MOD standards, typically referred to as mod, and they are designed to ensure that there is accuracy within the data and the models that are currently being used to assess the bulk electric system, and specifically in regards to reliability. And the main standards that we're looking at are going to be mod 25, mod 26, mod 27, and mod 32. This is kind of under the assumption that we're primarily talking to generator owners for this. So those are the ones that we're going to really be leaning into and really be assessing during this conversation. So what are the types of models that we look at during the mod process? And so there are three major kind of different types of models, and sometimes it's very key to identify them so that we're not comparing apples and oranges. So the first are generic models. Generic models are kind of what the name implies. They are models that are not specific to any one given type of inverter or generation, but instead are applicable to kind of a wide number. They typically are kind of less computationally taxing on computers. And so where we typically see generic models are on interconnection-wide studies. So the goal is to study a large amount of generation, a large amount of transmission, and we need, we can't have models that are too taxing on the system. We'll talk about EMT models in a minute here, but we couldn't have, a bunch of EMT models because it just fry a computer or it would take too long to run the study. So that's where generic models are really useful. They're nice, they're efficient, and they don't require a lot of kind of in-depth technical knowledge. UDMs are kind of the next level of complexity. So user-defined models, UDMs, are vendor-specific models that are more nuanced, more specific. Usually they are just this one inverter. You can't go above and beyond. You can't make it apply to something else. The goal is it is designed with one thing and one thing in mind. But because of that, they are nuanced with control information. They tend to have more specific information. And you can work with the OEM to make sure that the model performs really well within the areas that we're looking at. So if we're doing specific type of tests, you can kind of work with your OEM to ensure that those tests align really well with how the model and the settings within the models work. Whereas, kind of jumping back for a second, with generic models, if you are working with your OEM, you may need to understand where those models may deviate from kind of real world applications, because that will be important for knowing when and how those tests will operate and what's an expected amount of deviance or kind of expected abnormal behavior in those systems. Lastly, we'll talk about electromagnetic transient models, or EMT models. EMT models are typically used in areas with short circuit ratios, which are indications of weak grids, or with radial configurations with capacitors. So locations where stability issues may occur. So those models themselves, they usually are significantly more in-depth and tunable. And because there's more information, there's more parameters, there's more ability to kind of get into the nuts and bolts of the model. And usually EMT, those models are done in MATLAB Simulink, EMTP, or PSCAD as Gridsby uses. So those are the different types of models that we're looking at. And then we can talk about what are the actual standards. I mentioned them earlier. 25, 26, 27, and 32 are the big ones for this presentation. So we broke each of the standards into 3 different slides. We'll get to 2 right away, and then we'll talk about the kind of how to test each one later on in the presentation. So for the first slide for Mod 25, it's kind of the why. The why are we doing this? And the answer is we need to ensure that there is accurate information about the real and reactive capabilities of generators in the field, because we need to be able to model for planning, for different scenarios where there are disturbances on the grid. Those are all very important things to ensure. And so another thing to note is that we'll talk about what is the requirements to be applicable for Mod 25 to apply to your project. But another thing to mention for Mod 25 specifically is that it's looking at the generator's real and reactive capability, but it also applies to synchronous condensers' reactive power capability as well. But we'll see that more in who Mod 25 applies to. And so applicability, you can see generator units that are greater than 20 MVA, both for generator units and the synchronous condensers, if that's an individual generator. However, if the project is aggregate, has an aggregate nameplate greater than 75 MVA, then that will also be applicable Mod 25. And then obviously those will need to be connected to the BESS, the bulk electric system. As far as timing, when will you need to get your Mod 25 documentation in place? We typically say 1 year, not typically say. The standard is 1 year after COD, and then there's a requirement to update the Mod 25 submission every 5 years after that. There is an exception. If the capability of the project changes by 10%, then you will need to update your Mod 25 kind of as a direct result of that. For the next standard, and sorry, I should have mentioned this at the top, but feel free to raise your hand at any point in time, or feel free to drop any questions in the chat, and we'll get those read out loud, and then we'll answer them. Feel free to send them whenever you want. It usually keeps it easier to keep it on the slide that's relevant to whatever data or question you're asking about. And then obviously we'll have time at the end of the presentation as well to catch any questions that happen throughout the presentation. So just wanted to mention that now. I should have mentioned it at the top, so forgive me for that. And then with that, if there's no questions, we'll move to Mod 26. Mod 26 is, the goal is to verify that the model and the parameters within it, when in a dynamic simulation, accurately represent the generator's excitation control system or the plant's volt-var control functions. So we need to make sure that those are behaving properly. Once again, it's all about reliability. We need to make sure that these models are accurately representing what we're seeing in the field and actually operating in real life. And so that's kind of the goal, and hopefully the output will look something like the graphic on the side there, where the real data really nicely fits in with the model data. So who's applicable? What makes a project need to submit Mod 26? So this is one of the standards where the project is located is going to have an impact on applicability, as we'll see with Mod 27 coming up next year. So if you're in the Eastern or Quebec interconnections, then individual or aggregate generators with a nameplate greater than 100 MVA and connected to the bulk electric system will need to submit Mod 26. In addition, if you're in the Western interconnection instead, it's 75 MVA for both individual and aggregate generators. If you're in ERCOT, ERCOT's the one that splits it up with a difference between individual and aggregate. For an individual generator, you need to be your nameplate needs to be larger than 50 MVA. For aggregate, it needs to be larger than your nameplate needs to be larger than 75 MVA, and obviously connected to the bulk electric system. There could be a very dangerous drinking game with every time I say and connected to the bulk electric system. So be warned, drink water instead, something like this. As far as timing, this will probably be a little reminiscent once we start talking about 27 as well, but required within 1 year of COD. And there is the ongoing requirement to update every 10 years after that. And similar to Mod 25, there is a requirement to update the models and your submissions if things change. So for Mod 26 specifically, if you've made a change to a piece of equipment that changes the electrical characteristics, specifically for Mod 26, then you need to update your submission within 180 days of that change. On to Mod 27. Mod 27 is, the goal is to verify that models and model parameters in dynamic simulations accurately represent the generator's real power response to the system's frequency deviations. So essentially, the short version of that is, when frequency changes, how does your real power respond? And once again, we have kind of a graphic on the side of what an output may look like for that. And then similarly to Mod 26, these ones kind of echo each other for applicability and timing. So we'll run through it pretty quickly here. Eastern or Quebec, it's individual or aggregate. It simply needs to be larger than, nameplate needs to be larger than 100 MVA. For Western, your nameplate needs to be larger than 75 MVA for either individual or aggregate, and obviously connected to the bulk electric system. And then finally, ERCOT is the one that splits things up. So individual 50 MVA and a aggregate of 75 MVA. Once again, connected to the bulk electric system. For timing, required within 1 year of COD and updated every 10 years after that, with the exception of if you make a change to your equipment that would impact this specific standard, then you need to update within 180 days. For Mod 32, we can kind of move a little quickly through this slide. The goal of Mod 32 is to ensure that there are models in place as requested. So we'll go into kind of what those models are and what they look like on the next slide here. But it all comes down to modeling and ensuring that there is kind of reliability within the system. So in order to have the generators being modeled properly, we need to have the models. So moving on to the part two, we have what models are we looking at? We're looking at steady state models. We're looking at dynamic models. We're looking at short circuit models. And those are all, they come out of requests from the transmission planner or the planning coordinators. So the initial submission needs to be submitted within 90 days of notification by either the TP or PC. And it is scheduled for the kind of that resubmission every 13 calendar months. If there were no changes, you don't need to resubmit all of the models again. It is absolutely acceptable to simply just notify them either with a kind of a formal letter or sometimes even as simple as email communications indicating that there were no changes, therefore no models need to be resubmitted. So moving on to upcoming standards, because there are a few standards that are changing here. We're going to specifically talk about the mod standard here, and then we'll flag a few that we think are important coming up as well in the next slide. So the upcoming standard for mod is mod 25-3. This is about reactive capability. So what the standard is requesting is for a generator to provide the composite capability curve with 12 points of data and then documentation showing evidence of where that information is and the verification of that. So the typical 12 points are Pmin, 20% of max generation, 40% of max generation, 60% of max generation, 80% of max generation, and 100% of max generation for the leading and lagging scenarios. And obviously, this needs to be performed within 180 days of COD. So that's the upcoming mod standard. What we did here was obviously PRC is not mod. However, we've noticed that a number of PRC standards are changing in a way that we believe are going to maybe not inherently tie them to mod, but connect them much tighter into mod, or kind of lead into mod potentially. And that's because a lot of these standards used to kind of just be pass-fail type scenarios. But instead, what we're seeing is with kind of the new updates, there will be more of a requirement to demonstrate how your project responds, not just if your project responds. So kind of digging into it, mod 28 is a standard that focuses on disturbance monitoring. So the biggest emphasis is around equipment like circuit breakers, for example. And the standard not only increases the kind of data collection on these items, but it also will, depending on what the findings are, it may have impacts on the models as well. And so these models will need to be updated, may need to be submitted as evidence to demonstrate how the kind of like disturbance of the protections are in place in order to ensure that we are truly passing this. Once again, it's not just the kind of like check the box, yes, we passed, no, we did not. 29 is PRC 29-1 is it's kind of an update of 24 specific to inverter-based resources or IBRs. And what we're seeing is the previous submission 24 did not require any modeling. The big change is that modeling will be a requirement. You will need to demonstrate in dynamic simulations how your project responds to these frequency ride-through events and how your project responds to the voltage ride-through events. And then lastly, we have PRC 30, and that is specifically an evaluation of unplanned changes of power output. And so that can be things that are outside of our control, like if it suddenly is less sunny, or suddenly the wind kind of cuts off in a period that we expected for wind to be coming through. An example of something that may be less of kind of a natural event and more of a technical issue is if there was something like a protection system misoperation. And what we expect to see is dynamic simulations will be required to show, from the modeling perspective, how these projects interact with these kind of sudden changes of power output. So getting into how to prepare for tests and how to actually run these tests, that's kind of the next section here. So we'll get into preparation specifically. So the number one thing for preparing for a mod test is keeping in mind kind of the goal. The goal of all of this is to ensure that the models are as accurate as possible to represent the facility and the equipment. So we're going to be primarily focused on generators and inverters and the power plant controllers. So they need to be, parameterized as close to real world as possible. And so, going into the kind of next point in this slide here is the owners should make the effort to always get kind of the most accurate information as possible. And that specifically comes from how we interact with the OEMs. And so what we would request, or what we advise, is get model validation reports from your OEM. Obviously, kind of the closer to an as-built condition as we can get, or if we can get as-built, that it's ideal. But get the reports from your OEM. And that's very important if we're using generic models, because we need to know kind of where those deviations can occur. It's incredibly important if we're using UDMs, because we need to know what parameters are adjustable, what parameters are more set in stone, how those parameters interact, because very likely, if it is, unless it's a UDM that we've used in the past or that you have used in the past, it's very likely that it takes kind of a learning curve in order to get back up to speed with it. So a few things that we also suggest is requesting the parameter verification reports. And that's kind of what I was hinting at previously. But one of the things that is incredibly important is the OEM can show kind of the mapping between the model information and the equipment in the field. And so then the more that those line up, the better those align, the better the models are going to be. So then, if kind of preparation is mostly coordinating with the OEM, what type of documentation can we get in order to be prepared for a mod test? So we broke this slide into two, just because it got a little wordy if we put it all on one slide. So the first thing is, if we can get documentation for the generator and the PPC. So validated information, like we mentioned in the previous slide, from the OEM, kind of lining up those parameters. And then the next thing is something that can be done in advance, are spec sheets and ratings. Obviously, settings need to happen once the generator is kind of more operational, more likely to be approaching the issue for construction. But what we'd like to see are things like frequency and voltage ride-through settings, protection parameters. And then for the power plant controller, if we could get narratives and settings, that's obviously going to help, because a large part of all of the mod testing is tuning the PPC and in the dynamic models. Additionally, we we broke this out into 2 lines, but I'm going to kind of treat the last 2 bullet points very similarly. If we can get the factory acceptance tests or the FAT tests for your medium voltage transformers and your main power transformers, those are incredibly important. We can get images, it be those physical pictures taken out in the field, or digitized versions of the nameplates. Those are always also very important. And then usually more applicable to the MPT is if you have any tapping information. So de-energized tap changer settings or positioning, that's always very helpful, useful for making sure that the models are tuned properly. In addition to all of that documentation, there's kind of the information that is just general for helping create kind of the steady state model and making sure that we're not designing a model that sits outside of the parameters within your kind of project itself. So GenTie information and collector system information. For the GenTie, normal emergency ratings, line lengths, type of conductor, impedance values, your RX and B values. And for your collector system, very similar information, but primarily looking at things like if we can get line diagrams, table schedules, and then once again RX and B values for that. That's incredibly helpful. Cat banks are definitely one of those as applicable, but if it is applicable, specs, ratings, switching logic, all of that is helpful for ensuring that the project in the model accurately represents the project that's being built in the field. And then also single line diagrams for the substation, making sure that we have kind of a good understanding of what the sub looks like is very important. And then lastly, any interconnection agreements, be those small, be those large, and then any additional documentation that may kind of inform how the project is supposed to operate, and because that can help make sure that the model isn't doing things that directly violates that. Because we want to make sure that the model, the real world, and also your contractual obligations, all of those need to align. So that's all the things that we can do to kind of prepare for mod testing. So what does mod testing actually look like? So for mod 25, the typical test looks like we get the plant running at the active nominal power, and then we increase or decrease the voltage or reactive power controller set point in order to have the plant inject or consume reactive power. And the goal is to hit the plant's max LGIA required capability. However, what you may see is limitations from kind of equipment perspective. So that could be a limitation on the PPC. It could be a limitation from one of the other pieces of equipment, be it protection or the inverters themselves. And then lastly, it could be a limitation on the grid. So once again, we kind of showed a similar image in the previous slides talking about mod 26, but the idea is to be able to create a standard that will be submitted and will be compliant for all of that information and shows the kind of correct responses. So with mod 26, there's a little bit better of a visual for what that looks like. For mod 26, what the test looks like. Oh, sorry. The last step is obviously I'm stepping back from mod 26. The last step is obviously we collect all of that data and make sure that it aligns with everything that we see in them. So sorry, but jumping back to mod 26, I apologize for any confusion that may have happened there. Mod 26, what we do is we increase the voltage controller set points in steps of plus or minus 3 to 4% of the voltage nominal, and we record the response of the plant to those variations. There are situations where, due to some control logic, instead of using the voltage controller set point, you need to adjust the PPC's control reference set point for the grid voltage. But you still would apply the 3 to 4% nominal voltage step. You'll record the data, and then you fine tune those models, the power plant controller under dynamic simulations to tune in those models as tightly as you possibly can. And then lastly, mod 27. For mod 27, the way that you perform the test is you override the frequency value that goes to the PPC and replace it with a fake value to simulate the frequency excursions. So the goal is to, once again, record the response of how the plant adjusts to it. And then ideally, we take that data, we adjust the models as they've been submitted thus far, and we start tuning our parameters to make it so that as the plant does this, our model also does a similar thing. So that's kind of for especially mod 26, mod 27, that's how we keep those in line, is we take the real world data and we line it up the best we can with the data that feed into our dynamic models. As far as some of the kind of pitfalls or problems that we've seen, there's kind of one place where we've seen the most amount of problems, and that's with the primary frequency response. And so we've kind of narrowed it down to 4 kind of major things that we've seen as kind of a reoccurring problems in a number of projects. The first is in regards to active power curtailment. If the active power curtailment is applied to the set point rather than the actual active power that is being output by the generator, you can have issues. And so in order to kind of give an example of what I mean by that, if we have a 100 megawatt generator and its current set point is 100 megawatts, but it's not outputting 100 megawatts, it's outputting 50 megawatts. What you can see is the curtailment may be calculated incorrectly if we're using the set point versus if we're using the actual generation. So in that scenario, if we got an indication that we needed to curtail 10 megawatts, so if we're using the set point, well, it's going to say, well, the set point is 100 megawatts. You've been indicated that you need to curtail 10 megawatts. So we just bring it down to 90. And then it will see that the generation is at 50. So we'll say, well, no worries. We don't actually need to curtail after all. But what is true and more accurate is even though your set point is 50, your set point is 100, you're producing 50. If you're told to curtail 10, you should be curtailing 10 off of that 50. So you should bring down to 40. Another common error that we see is slow responses with the ramp up and ramp down settings. So the difficulties of kind of addressing this comes from the fact that there aren't a lot of standards in place that truly kind of dictate this, especially dictate this in a way that we believe is actually useful for a lot of projects. So, for example, the problem that we have is, defining how fast slow needs to be. And so in ERCOT, as an example, there's a requirement to deliver 70% of your response within 16 seconds. But even that standard, one of the few places where there is a standard that indicates how quickly you need to be doing this type of response, we still have found that that is typically too slow, and that a project may kind of miss the event that it's supposed to be responding to. The third point on here is the third point is kind of the opposite situation of the first point. And that's because it's specific to Drupe. So for Drupe, if you set the Drupe value based on your active power as opposed to your nameplate, then you once again will be calculating things kind of based on the wrong inherent values. So for the sake of kind of making math a little bit easier on myself, instead of using a 100 megawatt nameplate project, instead for this example, we use a 90 megawatt nameplate project. So a 90 megawatt project with a 5% Drupe that needs to curtail in order to correct for a 3 hertz deviation, what we'd expect is a 30 megawatt adjustment. So in the scenario where the settings are correct, what we would see is it says, it looks at the nameplate and it says, okay, your nameplate is 90 megawatts. You need to curtail 30 in order to correct for this frequency event. However, what we sometimes see is in the scenario where it's looking at your active power, the power that's being produced by the project, a Drupe setting may instead be calculated incorrectly. So going back to if we have the scenario where instead we're producing 45 megawatts, so we're once again operating at about half, what may happen is if you're not using the nameplate, you'd actually reduce less than you should in order to accommodate for that response based on the frequency event that's occurring. So what should happen is, even though you're producing 45 megawatts, you're actually looking at that 90 megawatt nameplate. So you calculate out the 30. So from 45, we need to scale it back down to 30 to, provide the proper response for that frequency event. And then last but not least, regarding deadbands, to ensure that the deadband is implemented without a step. So the issue is when there is a step into the Drupe curve, that can be incredibly difficult for the models and everything in place. So there is an inherent issue that if you have a project that is set up such that the Drupe band occurs and then you don't start from 0, then that can be a problem. So we want to flag it here. Of all of the problems we listed, it's probably the least consequential, but it is something to just mention that there can be problems that arise from that. Stepping away from the primary frequency response and just kind of more generic issues, what we see are the first two kind of have to do with how things get accounted for. So the first one is errors in calculating the internal facility losses when you're constrained on your delivery for the required reactive support at your high side of the MPT, and specifically for volt-var controllers. So what the issue is if you are not accounting for losses, then the project will not be able to provide your power factor requirements at the high side of the MPT. And so where that typically happens is if we see the volt-var controllers are monitoring the generator terminals instead of the high side of the MPT, that's where that kind of difference in losses can occur. Then you are not meeting your requirements. You're unable to hit your power factor requirements.
So Ryan was talking about errors calculating internal facility losses. So those are in the volt-var controllers. Sometimes you are controlling voltage in the high voltage side of the transformer, but you define the reactive limits, the Q limits at the inverters or at the generators terminals. So for example, you define there 50 plus 50 plus minus 50 mega MVS reactive there. So then when you need to deploy maximum reactive capabilities, if you haven't calculated the internal losses properly, what you get on the high voltage side of the transformer may be short of what you are supposed to deliver according to your interconnection agreements. So that's something that we have seen and is easy to fix. Is usually when we are testing, we fix it on the go, and we just increase those limits and to account for bar control functions. So that happens mainly when you have collocated facilities that are setting a common main power transformer. So you have meters in each of the in the low voltage side of the transformer for each of those facilities, and then to see what you have in the point of interconnection or high voltage side of the transformer, you do some compensation. Again, if those compensations are not done properly, or take into account that you have 2 or 3 or 4 different facilities going through the same transformer for the compensation, you could see errors in the modeling of the ball bar controller, or you can see things that is not what you were expecting. And the next one that is not an error, but is something that is difficult to model, is when the ball bar controller use dynamics values or the droop value, the Q max and Q mean values of the droop are adjusted dynamically. Usually they are based on a 0.95 power factor of the current active power production of the plant. So basically that what it does when you are modeling is that your KC value or the droop value of the controller change automatically with the generation. So that is difficult to model. I mean, it's not impossible, but you just can model one static condition, and you need to put in the report. The last one, here, what we have is a reminder that, I mean, there's no such a thing like a perfect model that is going to just, or that is going to predict exactly the reality of the plant. So what you are modeling, even the ENT models, you make assumptions. For example, you don't model exactly each of the generators of a wind farm facility, all the wind turbines that you have there, all the collector systems. So you do some assumptions, and you model an equivalent collector system and an aggregate wind turbine model for all the generator model for all the wind turbines. So in the case of a 0 voltage right-through condition, the model may say that you pass, and the reality may show that some of the wind turbines in the end turbines in the not the collector system, some of them may trip. So what you need to do, or what you need to know, is what is the reality, what are the assumptions that you have done, document those assumptions, and that way everybody is aware of how things are going. And again, the other really important thing here is what we were mentioning at the beginning. Each of the models, genetic models, user-defined models, or ENT models, they should come from your equipment manufacturer, from inverter manufacturers, wind turbine manufacturers, generator manufacturers. They should have come with a validation report where they have done a field type test, and they compare what is each of the models is reproducing, how each of the models is reproducing the reality. Again, we were talking about that the genetic models may not reproduce so accurately the reality of what happened in the field. The user-defined models could go a little bit more accurate, and the ENT models would be really accurate. So what you need to know, or what is really important, is to know how accurate are each of those models, so that you can make the decisions about when to use one model or the other. Okay, and again, all the models, I mean, no matter how accurate they are, here, garbage in, garbage out, you can have an ENT model that is really detailed, but if it is not set up correctly or with the right settings that reproduce what has been implemented in the field, it's a model that is useless, basically. So really important for each of the models or whatever is the model that comes with some kind of validation from the OEM, the manufacturer of the equipment, so that you know what are the capabilities and what are the how good each of the models is. Okay, and I think that's basically the presentation. So now, if anybody has any questions or wants us to talk more detail of any of the subjects, please. I mean, each of the standards, I think we were still sharing, or are you sharing? The requirements depends on the size of the plant, basically, and we were going through. So that's for example. Let's see. Mod 25. Here you have is for individual units greater than 20 MVAs or aggregated facilities with aggregated capacity greater than 75 MVAs. Mod 26 and Mod 27, it depends on the interconnection area. And these are in, both of them have the same requirements in Eastern or Quebec interconnection. Is for individual generators or aggregate generators higher than 100 MVAs. In the Western interconnection is again for individual or aggregate facilities of more than 75 MVAs, and in ERCOT is for individual generators bigger than 50 MVAs or aggregate bigger than 75 MVAs. So that is the applicability. New Mod 25 is gonna expand that, but just so far it's only that for Mod 25, and basically it's gonna be all these generators is if they are connected to the bulk electric system. The new Mod 25 is gonna be basically for any individual generator or aggregate facility greater than 20 MVAs reactive, 20 MVAs, sorry, greater than 20 MVAs.
And the next question was, are new standards applicable to old plants too?
And so the answer is, yeah, it's the same deal. What merits applicability is size and, you know, potentially voltage level, but it's based on project size. So if you are, you know, if your nameplate rating is higher than kind of the base level requirements, then you will need to be applicable to this.
But there should be some transition period, so where you have time to provide that information for your facilities. And in the case of, I don't have, but in the case of usually new standards, if your facility is too old and doesn't have the capabilities, usually the only thing that you have to do is to demonstrate or to demonstrate that your plant with some technical information from the manufacturer of the equipment or whatever, saying that your facility doesn't have those capabilities and should be fine. But if the facility has the capabilities, you have some time to adjust. And I don't remember to do the new test and adjust to that, to the new standards.